Okay, good morning to all. Welcome to this third lecture session of the course Engineering Thermodynamics. In this particular course, in our last lecture, we have studied about the macroscopic and microscopic approach for study of different thermodynamic systems. And then after that, we have had discussion on our thermodynamic systems. Okay, so there we have come up with the idea that anything which we consider inside a confined boundary, that boundary may be real or imaginary, and generally the thickness of the boundary is considered as 0. So anything which we consider, that particularly we call as nothing but our thermodynamic system. Now, if the mass of the system remains fixed and there is only energy interaction across the boundary, that particular type of system we call as nothing but our fixed mass system or closed system. If we are having a boundary across which both mass as well as the energy transfer is taking place, that particular type of system boundary we call nothing but our open system. Okay, and then we are having a very special type of system where we are not having any mass and energy interaction across its boundary. That particular kind of system we call nothing but an isolated system. Okay, now what we will try to do today, we will start our discussion with the concept of state and property. Okay, so first we will try to see that how we define the state of a system, what we call the state of a system, and then to represent that state of the system, what physical parameters are required, and these physical parameters or characteristics of the system at that particular given state are nothing but called as property of the system. Okay, so now if I take a simple example, what we see, water is a very commonly used liquid. So if you talk about water, generally corresponding to the atmospheric pressure and atmospheric temperature conditions, our water is having occurrence in liquid phase. Okay. However, if we keep the pressure constant and slightly increase the temperature, if we go somewhere close to, or I should say more than 100 degrees Celsius, if I keep the pressure as same, P atmospheric only, but if I make temperature greater than 100 degrees Celsius, then water will be actually changing to vapor state. Okay, and then we may also have solid state of the water in the form of ice if we keep once again pressure as atmospheric pressure only, and if we make temperature less than 0 degrees Celsius. So it means from this particular example, we can see that when we are changing the phase of a substance, or when we are changing the condition of pressure and temperature, we are finding that phase of substance is changing. Okay, so it means, and particularly what we do, phase is nothing but represents the some homogeneous quantity. So for example, in solid, water will be having some different structure, in vapor it will be having some different structure, in liquid it will be having some different structure, but within the entire solid you will be finding that there will be entire homogeneity. So we can call solid as one of the phase, liquid because there within the liquid itself water is homogeneous, there we can call this one as nothing but homogeneous phase. So it means these individual states where water is existing as solid, liquid or vapor, these individual we call nothing but as different phases of water. Okay, so these are called as nothing but different phases of a substance. So for example, in this particular example, we are having water as substance, so we will be calling these as nothing but different phases of this particular substance. Okay, now what will be happening, as I have already told you, that when we are actually changing some of the properties our phase is changing. So corresponding to each phase, obviously we will be having different conditions of pressure and temperature. As I have just stated you that if water is in solid phase, then temperature has to go below 0 degree Celsius. If it is in liquid phase under atmospheric pressure condition, then it has to be from 0 to 100 degrees Celsius, and in vapor phase it has to be more than 100 degrees Celsius. Okay, so the idea is any state of the substance or any state of the system which is in equilibrium, corresponding to that state, it means that state is not changing with time. By meaning of equilibrium, I am saying that that state is not leading to any changes within the system. So that particular point we call as nothing but state of the system. Okay, so what I am calling, now let me just define once again state. For example, if I have water in this container, so now obviously if I don't do anything, so this water will be remaining as it is. So at this particular point, I can call that nothing but my water is in the liquid state. Okay, so state is something which represents the particular characteristic, or I should say that represents the one particular instant at which actually our system or our substance is not changing. Okay, so if it is at some fixed configuration, that particular point we call as nothing but state of the system. Okay, and anything which characterizes the state, that particular thing is called as property of the system. So anything which characterizes, or I should say the characteristic parameters of the system, the characteristic parameters of the system are particularly called as nothing but the properties. Okay, so in case of thermodynamics, we are having many number of properties. So some of the properties which I would like to mention over here are nothing but examples of properties: pressure, temperature, volume, density. All these are nothing but the properties of the system. Like that, we may have a more number of properties, energy. All these are properties of the system, because these nothing but specifies or characterizes the state of a system. Or okay, so that's why one more important thing we have to consider over here, that corresponding to one physical situation of the system, we are having always fixed property. Okay, so for example, if I take water at say 1 atmospheric pressure, and say if I take at 25 degrees Celsius. Okay, now let us, so corresponding to this means we were having over here some physical state of this water. Okay, so corresponding to this physical state, whatever the characteristics of water we were having, these were nothing but 1 atmospheric pressure and 25 degrees Celsius temperature. Now, if I consider a situation that I have initially taken some ice, okay, which was having 1 atmospheric pressure and 0 degrees Celsius temperature. Okay, after that, what I did, I heated this ice, and I have heated till its temperature is reaching to 25 degrees Celsius. So what I will be finding, though I have changed the state of the system from 1 atmospheric pressure and 0 degrees Celsius to 1 atmospheric pressure and 25 degrees Celsius. So this is something, this state has been changed upon addition of heat, but now whatever initially we had taken at 1 atmospheric 25 degrees Celsius, whatever the matter physical state we were having, same physical state will be remaining in this second situation also. Okay, while we are actually obtaining these particular properties after heating our system. Okay, now let us consider another situation, that in this container initially we were having say condition of 1 atmospheric pressure and 90 degrees Celsius temperature. Okay, and after that what we have done, we have now cooled our system. Okay, we have cooled our system to make a temperature condition of 25 degrees Celsius. So now in this situation also, once again what will be happening, I'll be over here finding the physical state of the system, which will be exactly identical to the physical state of the system what we have taken originally. Okay, so the idea is that if we are having any specified properties, and if these properties are not changing, or in other words, I can say that if I am changing the system from one state to another state, but if my final state, so irrespective of whether I am changing the system either due to heating or due to cooling or any other type of process, if we are having same properties of the system, always we will be having same characteristics. Okay, so this gives idea that properties of the system are nothing but unique characteristics of physical state. Okay, so the idea now here, properties are nothing but unique characteristics of physical state of the system. So it means corresponding to a single physical state, we will be having only unique set of properties. Okay, and that will always remain same. So if we are changing our physical state to any other state, in that case, once again, the properties will be changing, and these properties will be remaining same irrespective of will remain same irrespective whether we have irrespective of the path how we have approached to that particular system. Okay, now while we define the properties, so we categorize properties into two different categories. So one side we call as extensive properties, and another side I'll be writing intensive properties. So we are having two different categorization of properties. One is extensive and second one is intensive. Okay, so extensive, in case of extensive properties, what we are having, these properties are nothing but directly linked with mass. So these are directly dependent on mass of the system or mass of the matter. Okay, and intensive properties are the one which are independent of mass of the system. So these are nothing but independent of mass. Okay, so how to determine whether a property is intensive or it is extensive, means whether it is independent of mass or whether it is depending upon mass. Okay, so the idea is what you can do, you can take a system or a matter. So for example, if I take m is mass of this system, now if I split this mass into two equal halves with the help of some imaginary partition. So what I have done, initially I have taken a single mass m. Now initially let us consider that the volume was V. Okay, now what I have done, I have splitted this mass into two equal halves. Okay, so what I have done, I have splitted this mass into two equal halves, and this I have done with the help of some imaginary partition. Okay, so in this situation, what will be happening, you will be finding that now what I have, initially I was having a single mass, then I have made this imaginary boundary. So after the imaginary boundary, now I will be finding two different pieces. Okay, so now I will be having now two different parts of the system. So if you now see what has happened, if I talk in terms of mass, then individual's mass has become m/2. Okay, if I talk about volume, volume has also become v/2. Okay, if I talk about density, so density is nothing but mass per unit volume. So initially your density was m by v over here. Now here if you talk about for first system also, if you do m by 2 divided by v by 2, 2 will be cancelling out, and finally we will be finding that density is remaining m by v only. Similarly for second system also, we are finding that density is remaining same, m by v only. Okay, if we talk about pressure and temperature, say initially P and T were the pressure and temperature. Here also we will be finding that after splitting this system into two parts, pressure and temperature of individual subsystems will be remaining same. Okay, so from here you can see the properties which have changed. These are nothing but referred to as the extensive properties, because these are depending upon that what quantity of matter we are considering. Okay, and the properties which are actually decreasing upon change of the mass or changing upon change of the mass, these particular properties are nothing but referred to as the extensive properties. Okay, so clearly you can see over here that our density, pressure and temperature are nothing but intensive property, whereas if you see about mass and volume, these are nothing but our extensive property. Okay, so one of the another property which we can consider at the moment, because you all are familiar with E, where E refers to the total energy of the system. So obviously total energy, if I split the system into two halves, so energy content of the system will also be actually decreasing. Okay, so it will be also changing with the proportion of mass. Okay, so that's why energy E is also nothing but extensive property of the system. Okay, so now there are few more things. What we do generally when we specify the intensive properties mainly we specify by using small alphabets. Okay, so we use small alphabets in order to specify the intensive properties. The only exception is pressure and temperature. So we use small alphabets except for pressure and temperature. So pressure and temperature are the intensive properties for which we have to write capital alphabets. Apart from these, each and every intensive property is specified with the help of small alphabets. Okay, and for extensive properties we use the capital alphabets. So here we use capital alphabet. So for example, you can see I am using capital E, capital V for specifying energy and volume, and here exception is mass. So except for mass. So for mass we use small alphabet. Apart from that, if we are having any extensive property, we will be always using the capital alphabet for that one. Okay. Now what we do, we are having one very interesting type of property. That particular property is something which is referred to as nothing but our specific property. Okay, so another interesting property is something which is referred to as specific property. So what is specific property? It is nothing but any property per unit mass is actually referred to as specific property. For example, I have told you that E is nothing but my extensive property. Okay, so E is extensive property, where E is nothing but energy of the system. Now if I have to write specific energy, so any property per unit mass is known as a specific property. So if I have to write specific energy, what I'll be doing, I'll be writing small e as capital E divided by m. Now why I have used over here small letter? I have used small letter because once we have divided any value of extensive property by mass. After that, what has happened, that property has actually converted into some specific energy, and now this specific energy is nothing but independent of mass. So this particular thing, because we have divided with mass, so that's why this is nothing but independent of mass. So if it is independent of mass, because of that, what will be happening, we can call this property as nothing but our intensive property. Okay, so as the definition of specific property is the value of property per unit mass. So that's why what will be happening, inherently the value of specific property will become independent of mass. So that's why every specific property is nothing but considered as intensive property of the system. Okay. Now let us come to an important topic. This particular topic is referred to as state postulates. Okay, so now the idea is how to specify, how to determine that what minimum number of properties are required to specify the state of a system. Okay, so for example, I have given you initially the idea of water. So in case of water, while I was talking about solid phase, liquid phase and vapor phase, I was always using two different properties. Okay, means I was using pressure and temperature. I was calling that at 1 atmospheric pressure and 0 degree Celsius, I'll be having solid. At 1 atmospheric pressure and temperature from 0 to 100, I'll be having liquid, and for more than 100, I'll be having vapor. Okay, so it means I was using two set of properties in order to specify the state of the system. So this state postulate specifies that how many number of independent properties are required to specify the state of the system. Okay, so generally what we do while we are defining the state of the system, we always employ intensive properties. Okay, so we employ intensive properties to specify state of the system. Why we employ intensive properties? Let me just explain. So for example, if you consider that you are having some fuel. Okay, so you are having some fuel, maybe gasoline, CNG, any kind of fuel. Okay, and say you are having 5 kg of this fuel. So if you are having 5 kg of this fuel, corresponding to 5 kg, say you are having nothing but 40 megajoules of energy within it. Okay, so if you use the same fuel in same physical state, but instead of 5 kg, if you take 10 kg of this particular fuel, what will be happening? Your value of total energy will be nothing but equal to 80 megajoule. So you can clearly see that in both these situations, what we are having here as well as here, in both the situations, we are having nothing but same physical state of the system. So if we are having same physical state of the system, then obviously our values of properties should remain same. But if we are considering the extensive properties which are depending upon mass, so then upon change of the mass, for example, if we take 2 kg water or 5 kg water or 10 kg water at the same pressure and temperature, its energy content will be changing, its extensive property, volume and mass are changing. So that's why while we define the state of the system, or we specify the state of the system, normally we try to specify state of the system with the help of intensive properties. Okay, so this is first point. Now another point is that if we are having a simply compressible substance, okay, so what I am saying now, you have to be very careful with this keyword, simply compressible substance. Okay, so any substance whatever we are having in absence of external forces, it acts as simply compressible. For example, if I don't have, what are the external forces? We know that nothing but our electric field, magnetic force, then gravitational field, all these are nothing but external forces. Okay, so if we are having a system or we are having a substance which is in the absence of external forces, means we are not having any external force coming into the picture, under this assumption we can say that our substance is nothing but a simply compressible substance. Okay, so now what will be happening if we are having so as per the state postulates, if we are having a simply compressible substance, we require two independent intensive properties to specify its state. Okay, so this is the idea that as per state postulates, if we are having any system which is involving a simply compressible substance, we require only two independent intensive properties to specify the state of this particular system. Okay, so let us take an example. For example, if I have a container and inside this container, say I have air filled. Okay, so I can write, if I measure the temperature of this air with the help of a thermometer, so I can say 25 degrees Celsius, and say if I measure once again the specific volume of this system, so I can say specific volume of 0.2 meter cube per kg are nothing but these are the two intensive properties which are particularly specifying the state of this particular system. Okay, so this state postulate is applicable when we are not having any transition between phases. Okay, so when we are talking about, or I should say when we are talking particularly about nothing but our single phase systems. Okay, so when we are talking about our single phase systems, there this state postulate is applicable. Now, if we talk about the another situation where we are having a container and inside this container we are having some vapor. So at the top of this container we are having some vapor. Okay, and at the bottom of this container we are having nothing but liquid phase. Okay, so at the bottom we have liquid water and at the top we have nothing but water only, but it is in vapor phase. Okay, so in this condition, if I only write say two properties, so this type of phase equilibrium for water under atmospheric pressure condition will be existing nothing but at corresponding to, this will be existing corresponding to our 100 degrees Celsius. So if I say that it is my 100 degrees Celsius is the temperature, and if I define some common specific volume, I cannot define, because what will be happening in liquid phase we will be having different density. So here density will be different, and in vapor phase here we will be having different density. So here density will be something else. Okay, so because of that what will be happening, we cannot only employ two properties. So two properties, okay, will not be sufficient to specify the state of the system. Okay, so what we require one more parameter, one additional parameter to specify the state. So that additional parameter may be that what fraction of liquid we are having or what fraction of vapor we are having. So any additional parameter is required to specify the state of the system if we are having phase transition involved. Okay, so that is particularly we will try to see in our next module while we will be discussing about nothing but our properties of pure substance. Okay, now what I will try to do, I will try to now give you the idea of thermodynamic equilibrium. Okay, because as I have already told you that we will be able to define the state of the system or property of the system only if system is in equilibrium. Okay, so that is the idea, that we will be able to, so state is only defined if system is in equilibrium. Why? So that is what I will now try to take up. So for example, if I have a system and inside this system, say I have some gas. Okay, so when we talk about gas, normally we try to take the example of a simple gas which is present in our atmosphere. So let us consider we are having nothing but air inside. Okay, so now when I'll be calling that this system is in equilibrium, the idea is that if say I have to specify any property, I am calling this as property as say y. Okay, so y is small y is my any intensive property, and I want to represent the value of this intensive property for this entire system. Okay, so if I have, say at this particular location, in this particular zone, I have the value of this property as nothing but y1. In some another area, I have value of properties as y2. In some another zone, I have value as y3. Somewhere I have value as y4. In some zone, it is y5. So like that, I have actually different values of y at various spatial locations within our system. Okay, so for this type of system, can I define the value of a single property? So that will be like not possible for us to specify the single value, not even by taking the volumetric average. Why? Because if we are having different values of this property y within our system, so because of that, what will be happening? There will be gradient existing in between the different zones, and because of these gradients, there will be some phenomenon which will be happening inside. Okay, so that's why, because at that point we will not be having the unique value of y, because of the gradients which are existing because of different values of y in various locations. What will be happening? We will be having changes in overall bulk property of the system. Okay, so that's why while we are defining the state of the system, for defining the state of the system, our system should be in equilibrium. It means that within the system we should not have any gradient of any property which is actually leading to, there may exist gradient in some situations. Okay, in some special cases there may exist gradient, but that gradient should not cause the physical phenomenon to happen. Okay, so that's why our state should be in equilibrium. Now this is very broad idea. When we talk about thermodynamics, in case of thermodynamics we specify one typical equilibrium. That particular equilibrium is known as thermodynamic equilibrium. So in case of thermodynamics, we will be able to specify the state of the system only if we are having thermodynamic equilibrium. Okay, so what will be happening? We say that our system is in thermodynamic equilibrium if it is following three criteria. Okay, the first criteria is that if our system is in thermal equilibrium. Second is if it is in nothing but mechanical equilibrium. and third criteria is if it is in chemical equilibrium. So if our system is in thermal equilibrium, chemical equilibrium and mechanical equilibrium, if our system is following all these three conditions, then only we will be able to say that our system is in thermodynamic equilibrium. And if our system is in thermodynamic equilibrium, in that case what will be happening? Obviously we will be able to specify the state of the system. Okay, now let us try to see these individual equilibriums with the help of some illustrations. So in first case I have taken a container, and inside this container I have taken some air, and I have considered a situation that at some point my temperature within the system is 250 degrees Celsius. At some point my temperature is say 100 degrees Celsius, somewhere it is 50, somewhere it is 300, somewhere it is 350, somewhere it is 500, and somewhere it is say 120. So now what will be happening? If you see within this system, temperature at various locations is different. Okay, so because of that, what will be happening? We always know from our basic understanding, if we are having the difference of temperature, then in that case what will be happening? Between two different locations, there will be existence of nothing but temperature gradients. So in this first situation, we will be having existence of temperature gradient. Temperature gradient is nothing but variation of temperature with location. Okay, so the gradient of any parameter we refer as nothing but variation of temperature with location. So if we are having any parameter whose variation is actually happening with the location, so with that particular thing we call as nothing but gradient of that particular parameter. Okay, so when we will be having the temperature of gradient, obviously within this system we will be having nothing but heat transfer process. Okay, so we will be having heat transfer process. So if the heat transfer process will take place, obviously what will be happening? Physical state of the system will change. Okay, so in this situation what will be happening? Physical state of system will change. So if physical state of the system is changing, it is in the transient phase. We cannot define the state of the system and we cannot specify a single unique property for that system. Okay, so that's why for thermal equilibrium to take place, what has to happen? Within the system, I should have everywhere, say if I have 150 degrees Celsius, so everywhere the temperature should be 150. If within the system everywhere temperature is 150, in that case what will be happening? We will not be having any heat transfer process. So any process because of the thermal gradient. So that's why we can say that our system is nothing but in thermal equilibrium. Okay, now let us try to see the another type of equilibrium. So another type of equilibrium we call as nothing but our mechanical equilibrium. So mechanical equilibrium is something which is linked to the gradient of pressure. So if we have, say this is our piston cylinder arrangement, and over the inside this piston cylinder arrangement we are having some gas field. Okay, so here we are having some gas field. So now say I have some weight W on this piston. So if my system is in equilibrium, then obviously what will be happening? Whatever the pressure, this gas will be exerting on different faces. Okay, so that pressure everywhere will be same. So this pressure will be same if our system is in equilibrium. Okay, so if we are having gradient of pressure within the system, for example, if I take a scenario that I have same situation, okay, I have same situation, but let us consider in this particular bottom zone, we have high pressure. Okay, means at some instant, say that high pressure has been created upon the addition of the heat. From here, you are adding the heat, because of that some high pressure is created at this location. Okay, and here in some other portion, you are having low pressure. So what will be happening? Because of this difference of pressure, there will be mechanical motion of the medium, and that mechanical motion of the medium will try to move piston either in up or down depending upon the overall situation of the system. And under this condition, what will be happening? We'll be having actually changes in the physical state of the system. So that's why the condition is that if we have mechanical equilibrium, then pressure everywhere within the system should be same. Okay, now only one small issue comes when we deal about our of our big systems, large systems in presence of the gravitational field. Okay, so for example, if I have a large container, and in this container I have, say, water field. Okay, so if we are having water field, then even in the equilibrium position, though if this water is nothing but in static conditions, obviously this will be nothing but in our equilibrium position. Okay, so in this type of situation, what will be happening? Depending upon the height at which we are actually seeing, we will be having nothing but high pressure at bottom, and as we will be moving towards the free surface is nothing but outside we will be having air, here we will be having water. So the interface boundary in between air and water I am calling as free surface. So in this particular type of situation, what will be happening? If our height is significant, this h value is very large, and gravity is present, obviously in our ambient, if we are taking any system, we will be having always gravitational field. So there we will be having actually hydrostatic pressure acting. So because of that, we will be finding pressure profile will be something like this. So we will be having high pressure at the bottom, and as we will be moving towards the free surface, the value of pressure will be actually decreasing. Okay, so that is the only thing, that if we are having the effect of elevation into our system, okay, in presence of the gravitational field, under this assumption we will be having actually different pressure within the system, but because of the change of pressure also, so we will be having different pressure, but because of the change of pressure also, our system will be in equilibrium. If we don't have the effect of elevation, then obviously throughout our pressure should be same. Now the question comes, though we are having over here the gradient of pressure, still why our system is in the balanced state? The idea is system is in balanced state because this pressure is actually holding the weight of water column. Okay, so let me just explain this idea in more details. So what will be happening? I have taken this as situation. So initially I referred that here pressure is high and there pressure is actually low. Okay, so and above we have over here nothing but as some water column. So what I am saying, that at this particular point pressure is highest. So why pressure is highest over here? Here pressure is highest because if I draw the free body diagram, so in order to draw the free body diagram, what I'll be doing? I'll be taking nothing but this liquid column. Okay, so what is happening? The weight of this liquid column is actually acting in downward direction, which is equal to m into g, and from here bottom some pressure P is acting. So I am calling this pressure as, say, bottom pressure, and multiplied by area of this bottom face. So that will be the force. Okay. Now, if I want to measure the pressure at any particular intermediate location, so at any intermediate location, say if I take that particular location as nothing but the half of the height. So for half of the height, what will be happening? My weight will become half. So because of that, downward force now will be nothing but equal to mg by 2. So if downward force is mg by 2, so the pressure at mid location, if I write this as P mid into A, so in that case, what will be happening? Obviously, because it is this mid plane is only balancing the half of the weight of the liquid column. So that's why here pressure will be half to that of the pressure at the bottom. Okay. So the only thing that if we are having the effect of elevation into our consideration, in that case, pressure will be varying with the elevation, where bottom point will be having highest pressure, and as we move towards the top, our value of pressure will be actually decreasing. The only thing under this situation also, we will be having the static equilibrium or static mechanical equilibrium. Why? Because whatever this pressure is generated, that is actually high pressure zone, that is actually balancing the weight of the liquid column. Okay, so that's why we may have variation of pressure if we are including the effect of elevation under even the static equilibrium condition. Okay, then comes the, so this type of equilibrium we have already defined as nothing but our mechanical equilibrium, and then comes the idea of another third type of equilibrium, which I have called as nothing but chemical equilibrium. Okay. So in case of chemical equilibrium, what I would like to do, so this type of thing is particularly involved when we are having species transport, or I should say the chemical reactions involved. Okay, so when we are having chemical reactions involved, for example, if I have a combustion chamber, inside this combustion chamber I have added air and I have added over here some fuel. So obviously fuel will be having some composition. So fuel may have hydrogen, carbon. Okay, so and in the air also we will be having different chemical compositions. Okay, so now what will be happening while this air and fuel will be reacting with each other? So obviously different phases, whatever we have considered, these will be having different chemical potentials and chemical affinities to interact with each other. And if they are having the chemical affinity, or I should say the chemical potential, so because of that chemical affinity or chemical potential, what will be happening? Some reactions will take place, and these reactions will be nothing but changing the phase composition. Okay, so these will change the phase composition. So if the phase compositions are changing, obviously we cannot define some fixed value. Okay, so what should happen for chemical equilibrium to establish? We should not have any chemical affinity or chemical potential between our different mediums. Okay, so if that chemical potential we are not having, in that case what will be happening? We will be having actually our chemical equilibrium established. And if in a situation we are having all three types of equilibrium, thermal, mechanical and chemical, we can say that our system is in thermodynamic equilibrium. And if our system is in thermodynamic equilibrium, then only we will be able to specify the state of the system, and we will be able to define the bulk properties for that particular type of system. Okay, now let us try to see the definition of a few basic properties. So the very first property which I want to take over here, let us discuss about specific volume. Okay, so we know that specific volume is nothing but, in broad sense, we call as volume per unit mass, because any specific property is nothing but per unit mass. Okay, now we already know the definition of density. So if I have to represent a letter for specific volume, I have to write small v. Now we know that density is nothing but mass per unit volume. So I can say that density is nothing but reciprocal of the specific volume. Okay. So while we are talking about specific volume, what we have to do, we have to consider this specific volume as nothing but, we have to consider this as specified at some particular point. Why we have to specify this at a point? Because we have already seen that if we go into molecular level, So at the molecular level, what will be happening? We will be having a situation where we are having molecules and we will be having certain portions where we are having void spaces. Okay. So if we are like pointing to a void space, there obviously we will not be having, or we will be having some weird value of the specific volume. And if we are pointing towards a molecule, then we will be having some another value of the specific volume. Okay, so that's why a specific volume is something which actually depend upon the specific location of the matter. So because of that, what we want to do, we want to basically obtain the value of this specific volume corresponding to some specific point. So when we do this, when we are pointing towards some specific location, under this situation, what we do, we try to write the definition of specific volume as nothing but limit delta V. So this delta V, I have to now mention something. So here I am writing this as my delta V divided by delta M. And here I am saying that this delta V is approaching to, so normally when we want to specifically locate mathematically to a point, we write this as delta V tending to 0. Okay, but in this particular situation, we will not write delta V tending to 0. Rather, we will write delta V tending to some value delta V dash. Okay, so why we are writing this delta V dash and what is this delta V dash? Let us try to see. So if I plot delta V divided by delta M as function of, so here say if I call this as nothing but delta V by delta M. So if I represent this delta V by delta M as function of volume, say here I am writing this as this delta V. So if I represent this as function of volume, what will be happening when my volume is exactly 0, means this delta V is approaching to 0. So I have nothing but a point. Okay. So I may come up with a situation where I am referring this particular volume, very small volume, which is close to 0. I may end up a situation that this volume is nothing but corresponding to some void space. Okay, so if this volume is corresponding to some void space, then obviously we will be having 0 mass at this location. So if we are having 0 mass, so this particular small volume divided by 0 will be becoming nothing but equal to infinity. Okay, so the idea is we will be finding the value of volume as very large, close to infinity. And if we end up on reaching a position at the center of a nucleus, okay, so if we are ending up in a situation where we are exactly locating ourselves or we are pointing our volume exactly at the nucleus, okay, so what will be happening? We normally try to consider that all our mass is concentrated at the nucleus, so we will be finding some finite mass over there, and we are having our value of volume very small. So because of that, what will be happening? Our value of del V by del V and del M will be very small. Okay, so we will be finding that if our value of delta V is less than some value, less than some specific value, delta V dash, in that zone we will be having significant oscillations in our value of specific volume, which will be varying from infinity to some finite value. And after this delta V dash, we will be having almost constant value of our specific volume. Okay, so after this delta V dash boundary, we are having after that nothing but almost constant value. So this delta V is nothing but the critical volume at which our continuum assumption becomes applicable. Okay, so this is the volume scale at which our continuum assumption become applicable. So if continuum assumption is becoming applicable, we will be considering that everywhere we are having homogeneous matter and we are not having any void spaces. Because of that, while we specify this limit in the definition of specific volume, we refer to some value delta V dash instead of delta V refers to 0. Okay, so probably now it's time for your next class. So that's why I'll be stopping at this point, and we'll have further discussion in our next session.